All right, so we just looked at an example of an object, the triangle, that had a uniform density, but that had a non-uniform shape. It wasn't just like a nice symmetrical rectangle or something. We can also have something that has a relatively symmetrical shape. So this is just sort of like a brick, but it has a non-uniform density. And so if this is all made out of the same material, you would expect the center of mass to be right in the middle. But if I actually try to balance it at the middle, we'll see this is not going to work. If I let go, flops over to the this side. And the reason for that is because the what this is made out of varies depending on its position. You might actually be able to see in the video, I don't know if that's showing up, you can actually sort of see there's different materials inside of here. So the way I made this is there are a couple of rulers in here to provide a sturdy base. And then on top of that, I took a bunch of pencil erasers, so like rubber erasers, and I cut them up and stacked them into a roughly parabolic curve. And so you can see there's more pencil erasers here, and then it gets thinner here, and that actually follows a parabola. And then I just fill up the remaining volume with really lightweight insulating foam. The erasers are way denser than the foam, and so there's a lot more mass over on this side. And then I just tape the whole thing up. So now we have an object that's relatively uniform in shape, but it is not uniform in density. And so we'd like to figure out where the center of mass is. And knowing that there's more mass on this side, that would explain why the center of mass is not in the middle, because the center of mass has got to be closer to the edge with more mass. And so somewhere in the middle has got to be, or somewhere not in the middle, somewhere over towards the heavier side has got to be where the center of mass is. And so in order to be able to figure that out, we need to know some things about the object. And so on the top of here, I've got some measurements for you. The total width of the bar is 32 centimeters. And we're going to work in meters, that's 0.32 meters. But 32 centimeters, just over a foot, because the whole thing is stacked on top of a couple of rulers that are just over a foot long. And then the other thing is we need a way to describe what the density is at any given point, because we got this parabola of erasers, and so the density is continually increasing as we work our way along. And so that's defined by this function. So gamma is what we use for the linear density function. That's telling us how many kilograms we have per meter. So you can, if you took like this little bit right here, if you figured out, what fraction of a meter is and what fraction of a kilogram is, and you divide that out, you'd get the density defined by this equation. The position, it's based on position x, measured from the end, the light end, I believe. And so the density at any point along here in kilograms per meter is given by this function. The function has two parts. The first part's a constant. That is from the fact that the rulers that run along here have some mass that actually in a meaningful way contribute to the center of mass. And those rulers are uniform all the way across. And so part of our density equation is just a constant. But then we have this variable term, 35x squared. It's x squared because, like I said, it's a parabola. And so as we move along, as our x position increases, we have this square function affecting how many erasers we have, which is causing our mass to increase according to x squared. And so that is the entire density function. Hopefully that's showing up. Gamma equals 0.24 plus 35x squared. We'd like to use everything we've learned so far, all of our equations, all of our relationships, to try to actually calculate two things. I want to know what the total mass of the bar is, and I also want to know where its center of mass is. So what is the mass and where is the center of mass? And to help you sort of check your work, I'll show you, we can see roughly what the center of mass looks like. So if I find the point where it balances, somewhere around there. Okay, so we can't actually, you can't measure that. You can see where my fingers are. So, if the whole thing's 32 centimeters, roughly that far over is what you should be getting for where the center of mass is if you're doing all the math correctly. And so the answers and the work are going to be in the next video. But before watching that, I'd like you to try to actually solve this problem on your own. Remember, there are two things that you need. You need to find the total mass of the bar because that is a valid problem. And then you also need to figure out where the center of mass is. So two different things we can do with the information we have. This is the sort of, problem could very easily appear on an AP test. There are two integrals that look very similar that deal with stuff like this where we have a non-uniform density. One calculates center of mass, another one looks very similar. It's used to calculate the moment of inertia or the rotational inertia of an object, which we'll talk about in a future unit. But it is fairly common for one of those two integrals to be on the test somewhere. And so this is definitely something you want to be able to do on your own. That said, this is the first time we are doing this. And so if you're not able to do it on your own this first time through, that's understandable. What I'd like you to do is make sure you can do as much as you can before watching the answer video. And then if you think you have an answer, you can just watch the answer video all the way through. But if you don't have a final answer, watch as much of the answer video as you need to get an idea of what the next step is. And maybe you don't learn enough to solve the entire problem, but you at least realize, hey, if I pause the video here, I bet I can figure out the next few steps ahead of Mr. Malm, or I can solve this equation before Mr. Malm, or I can do this substitution before Mr. Malm. And if at any point you get to a point in the solution video where you can work ahead of me, pause the video, get as far as you can. If you get all the way to the end, great. If not, get as far as you can, and then unpause the video, check your work, and continue watching the solution video.